Exercise 41.9. This exercise is to be solved manually. Consider the region enclosed by the graphs of y equal to the square root of quantity 2x minus 1, 4x plus 3y equals 4, and 12x minus 5y equals 12. Part A. Sketch a quality graph of the described region and provide a graphic approximation of the area of the region. Part B. Provide a calculus calculation that yields the exact area of the region. Part C. Assess the correctness of parts A and B by examining for consistency between the two results. Part A. Sketch a quality graph of the described region. Provide a graphic approximation of the area of the region. Okay, this region is enclosed by 3 graphs, so it's a bit complicated, and at first it's not even clear on what kind of coordinate system to put in place, so it's as if a little thumbnail sketch, a little thinking graph is required before we start the real graph. Okay, starting with this first equation, y equal to the square root of 2x minus 1. What about that? One generalization that comes to mind is anytime you have an equation of the form y equals to the square root of a linear expression in x, as we see here, you know right away the graph is going to be a semi-parabola having a horizontal axis of symmetry, and the x-coordinate of the vertex is determined from solving the radicand equal to 0. The term radicand, by the way, refers to the expression underneath the square root sign in this case. Okay, so having thought that, I could go to work here a little bit. Alright, now I need to solve 2x minus 1 equals 0. Real easy, of course. That gives us x equals to 1/2 there. So there's the x-coordinate of the vertex. And by the way, the y-coordinate would, of course, equal, well, 0 in this case, substituting it into there. Alright. It'd be nice to have a few more points, of course, for this semi-parabola, and for that I find myself just sort of tabulating the old-fashioned way. So we already know about 1/2 get 0. What else will I do here? I want to choose x's so that I have a perfect square radicands here. So like x equal to 1. That means y equals square root of 2 minus 1, square root of 1, that's 1. Okay. I would like this radicand to be a 4. So let's see, 2x minus 1 to be 4. X will need to be 5/2. And then I get y equal to 2. Alright, so there's enough to sort of get the thumbnail going. It's just an informal graph to see what is going on here. So maybe even up here, let's see, just really rough. Okay, so let's see, we got the 1/2 0 for the vertex, and it's 1 1, and then it's 5/2 2, 5/2 2.5 2. Okay, something about like there. Alright, and let's see, how about the next item here? This will be this equation here. Okay, linear in x, linear in y. We know that's a straight line. Maybe pick up some quick intercepts here to get this rolling quickly. Let y be 0. X is then 1. Okay, there's there. Let's let x be 0, and then y would be 4/3. 1 1/3. Okay, about there. Okay, and kind of a straight line to help us think a little bit about that. And then move on to the third equation here. Okay, this is going to be a straight line as well. Alright, how about some quickie intercepts? Let y be 0. X is 1. And then let x be 0. And then y becomes, let's see, negative 12/5. negative 2.4 around here. Sketch straight line. Okay, from the rough thumbnail, it looks like we have something in here going on. So now this gives us some ideas about how to set up our final coordinate system with our nice quality graph. Most of the action is going to be here in the first quadrant, and we want to kind of zoom in quite a bit here. It's a rather small region, so to get an accurate estimate, make it big. So we're going to probably scale this. Let's see, maybe having x and y go out to as at most 3, and then perhaps scaling. Let's see. Maybe I'll go with 1 centimeter equals 1/5 unit, 0.2. That might make things large and fits in the paper. Okay, I'll set that up. Alright, looking pretty good so far. Some details still need to be put in for this to be a quality graph, and for instance the intersection points are important here, so let's get those. Just by graphing, we actually ran into the idea that 1, 0 is the intersection of these two lines, so not much work to be done for there. However, we need here and we need here. So let's work on that next. So first, considering the intersection of the red curve and the blue curve. That's the intersection then of y equals 2 the square root of 2x minus 1 and 4x plus 3y equals 4. So now we have a nonlinear system here to be working on. Okay, since the y here is already solved for, it looks like a substitution method might work pretty easily. Take the y here and replace it in this second equation of the system. We arrive here. Alright, got ourselves a one variable equation, and it is a radical equation. Okay, quick algebra review. How do we solve those? First, isolate a radical. Second, square both sides to eliminate the radical. And importantly, step 3, check for and discard any extraneous solutions. Okay, so let's start first by isolating this radical, or at least an integral multiple of it. Alright, and it's time for squaring both sides to eliminate the radical, but it's a bit of an algebraic risk in that extraneous solutions could now be brought in. By the way, that term extraneous solutions, that means it's a solution that appears at the end of your solution process, but does not solve the original equation, is not then a solution at all, and must be discarded. Okay, so let's go here. We then have a okay, let's see, sitting here is really 18x minus 9. Let's set all of this equal to 0. Could this be a perfect square trinomial? Okay, here's the 4x quantity squared, here's the 5 squared. Let's see, 2ab would then be 4, 5, 20, 40. X then? No, it's not a perfect square trinomial. Okay, so let's try going with the structuring the binomials. Perhaps we try this kind of structure. And 25, okay, not too many choices here. Good. We have to get a negative here, so we're looking at a -5, -5, or a -25, -1. The negative 5, that would have been the binomial. Perfect square trinomial, we talked about that. That doesn't work. If we were to try negative 25, negative 1, that's a negative 100. Okay, and negative 104, not working. Okay, cancel that. Let's see. Besides the 4x initial first terms, we could try 8x, 2x. All right, let's see. What if we go with the negative 5 there? Outer terms minus 40, inner terms minus 10, minus 50x. Okay. Here we've got a factorization equal to 0. We now have solving each factor equal to 0. X equals to 5/8, or here it gives us, let's see, x equals to 5/2. X equals to 5/2. Okay, well, got to check for extraneous. This means, well, normally this would mean take these numbers, put them back into the original equation, see if they make it true or not. But you know what? We actually have available to us a graphic check, since we have already graphed this. And by looking at our graph right now, we can see that, well, an x corresponding to 5/8 looks very consistent with the graph. The x equal to 5/2 is nowhere to be seen. So this one here, extraneous, and that means discard that. And this is our only keeper here. Alright, well, the corresponding y of this, by the way, that we could use either equation. I'll go with this square root here. I'd have y equal to 2 of these. That would be 5/4 then. Minus 1. It's a square root of 1/4. That's 1/2. Okay, so 5/8, 1/2 labels the intersection point. And time to now seek this intersection point. So algebraically, we're looking for the intersection of y equals 2x minus 1 and 12x minus 5y equals 12. Once again, a nonlinear system, and as in the previous one, looks like it's already well set up for substitution. Let's go with that. Okay, this leads us to another radical equation. So, as before, let's get a radical isolated, or at least an integral multiple of a radical isolated. Okay, time to square both sides. Okay, let's see, this, if multiplied out, would give us 50x minus 25. Let's set all this equal to 0. Okay, so now we have this quadratic equation. A factorization, hopefully. Let's see, is this a perfect square trinomial? Got squares here and here. It's a possibility. Here, this is the 13 squared. Here, of course, would be the 12x squared. So let's see, a 12 by 13. Let's see, that's 144, 154, 156. And then double that, that would be 312. No, we have the minus 338. Okay, not a perfect square trinomial. Alright, well, let's continue trying to factor it as a pair of binomials. And, well, let's see. You know, for that, the first structure. Okay, one good thing about this only being 13 squared is there's not a lot of trials over here. We already saw the 13 failed. The other item would be to try a 169 and a 1. We need to have minus minus. Okay, 12 by 169 is hugely negative. Okay, no chance there. Okay, this is not working. Let's scrap that. By the way, 12, which is a 4 by 3, it makes it 2 squared by 3. The 144 then becomes 2 squared by 3, 2 to the 4th, 3 squared. I want to get this 144 fully factored so I can keep thinking of all the possible structures to use as a pair of binomials. Okay, so 12 and 12, not working. How about we, okay, the 2 to the 4th and the 3 squared. 2 to the 4th, that's 16. x, and the 3 squared is the 9. How about this structure here? Okay, let's see if we did a minus 13 minus 13. Now we'd have outer products to be 13 by 16. And the inner products 9 by 13. Let's add these up. 325. No. Okay. If we try the extreme situation of the minus 169, it's either paired with a 16 or a 9, which will be a hugely negative number, way more negative than negative 338. So no point going further with that idea. I suppose we cancel that structure as well. Alright, let's try moving one of the factors of 2 over to here. So that makes this now down to 8x. And this makes this up to 18. Okay, let's see. What about that? Okay, 13 by 18x. 13 by 18. And then the 8 by 13. Oh, okay, that's working. Okay, this is work. This is a factorization on the left-hand side. Back to our equation, a factorization equal to 0. Solve each factor equal to 0. This one gives us an x equals to 13/8. Or this one gives us an x equals 13/18. Let's look back at that graph. Graphically speaking, this intersection appears only at one possible point. It's because we know we have a semiparabola and we know we have a straight line and we see about how they're intersecting. So the only realistic possibility, the one that's graphically consistent, is the 13/8. This is extraneous. Graph is nice, saves us the trouble of having to do an algebraic substitution into the original equation. And extraneous means discard. Not a solution after all. And the corresponding y that goes with this, I'll grab the radical, substitute it in there. This is the square root of 2 of these. Okay, 13/4 for 2 of them, minus 1. Okay, that's minus 4/4. This is the square root of 9/4. Okay, 3/2. Great. Okay, onto the graph to label this. Also checking that y out for consistency, 3/2. Here's 1.6. This is 1.4. That's pretty reasonable for our graphic consistency. Okay, everything's looking pretty good here. Now this is a pretty good graph. It's got all the equations graphed, labeled, the key intersections labeled, axes scaled and labeled. It's all here. Okay, I see I have both axes scaled the same, so I can draw any shape I want to, and I can just work off a nice simple ruler measurements to approximate its area. I think I'll take advantage of these straight lines here and here and start finishing off with a trapezoid that seems to fit the region. Just choose about here for a starting. I'll go with a dashed line. Now here's the remaining side of my trapezoid. I want to make it so that I leave a void that will be filled by this overflow. Alright, so I'm going to actually keep this point. I think about there has a void that will get filled by that overflow there. So I'll sketch in this. Okay, so now we can make the claim that the area of the enclosed region is approximately equal to the area of this dashed trapezoid. And a trapezoid, a good geometric shape to memorize its area formula for. Easy to remember, average base times height, so 1/2 b1 plus b2 times h, and that is about equal here to 1/2 times, okay, let's see, b1, call it right here. Now remember, these are being scaled at 1/5 of a unit per centimeter, right? So here I've got 8.5 fifths. Okay, so let's see, there's 8/5, that's 1.6, and another 1/10. So we'll say that's 1.7. Base 2. Okay, it looks real close to 4 centimeters, which would be 0.8. The height or altitude of this looks, okay, pretty close to 2 centimeters here, so that's 0.2, 0.4. I'll just call it 0.4. .50 square units. Okay. Part B. Provide a calculus calculation that yields the exact area of the region. Okay, in the past we've always been slicing up our region with usually thin vertical rectangles and then formulating the area of one of those rectangles and then summing the rectangles. In this case, we could do that. However, looking at this region, there's something special kind of going on here, and that's due to these straight lines here. Looking at this region, it is kind of possible to notice there are some triangles sitting here as voids, and anytime you have a region which either consists of plane geometry figures or has voids which are plane geometry figures, it's time to think about taking advantage of some plane geometry within the calculation as well. So in this case here, I sort of imagine dropping down a vertical line, and I'll put it in dots here. And then another vertical line I'll put in dots at the other end point of this region. Alright, so now the region whose area we're trying to calculate, I could think of it as the region of everything below the graph of y equals to 2x minus 1 between x equals to 5/8 and x equals to 13/8. Now that area would be very simple. The sums of the thin vertical rectangles always lead you to that same famous result where the area is simply the definite integral from 5/8 to 13/8 f of x dx. A way to think of the graphic meaning of the integral of f of x, just f of x dx from a to b, the algebraic area under the curve. Okay, so it's all of that subtracting this cross-hatched rectangle and subtracting the area of this cross-hatched rectangle. I think that'll actually lead us to simpler calculations rather than trying to deal with the somewhat complex thin vertical rectangles that result in the more direct route. So let's use the plane geometry here and write our formulation for area that way. Okay, so the strategy here is that the area of this region is going to equal the area of the entire region below the graph of y equals square root of 2x minus 1 from x equals to 5/8 to x equals to 13/8. Subtract the area of that left cross-hatched right triangle. Subtract the area of the right cross-hatched right triangle. And so that will give us, this is equal to, that'll be a definite integral, 5/8 to 13/8 of square root of 2x minus 1 dx, and then we'll minus 1/2 base times height of the first triangle. I guess we'll call it B1, H1, and then we'll subtract 1/2 B2, H2. That'll equal, alright, these will be subcalculations. Here are first subcalculation. Let's go ahead and deal with this definite integral here. Okay, chance for a little bit of U-substitution, I suppose. We could say here U equaling 2x minus 1 du would be then 2 dx. Don't have 2 dx. Many ways to do this. My favorite way is to just bring in a 2 dx, but tend to compensate out here to make up for that multiplied by 2 there. Then, what about this? X equals to 5/8. That implies that U would equal 2 by 5/8 minus 1. Let's see, so that would be 2 by 5/8, 10/8 minus 1. Okay, 2/8 or 1/4, of course. And the x equals to 13/8. That's going to give us a U equal to 2 of that, 26/8 minus 1. Cancel, cancel. That's 13/4 minus 1, known to us as 9/4. Make this look a little nicer, like we really did cancel that. Okay, and so now this definite integral becomes, the 1/2 stays. It's going from 1/4 to 9/4 of square root of U du. Okay, square root of U, that's like U to the 1/2, power rule. So we have the 1/2, that would give us a U to the 1/2 plus 1, 3/2. Divide by 3/2. To divide by 3/2 is to multiply by 2/3. And this goes from 1/4 to 9/4. Okay, so this starts to look like then. We have, let's see what's left over here, 1/3. For the 9/4 calculation, going to the 3/2 power minus a 1/4, going to a 3/2 power. Okay, you know what? 9/4, not just any old number, happens to be 3/2 squared. So it's that going to the 3/2, and 1/4 is actually 1/2 squared. Now we can take advantage of some laws of exponents, multiply these exponents. Just the 3 is left over, 3 cubed over 2 cubed. That'll be 27 over 8. Here, 2's cancel. 1/2 cubed, it's 1/8. Okay, so this turns into 1/3 times 26 over 8. Cancel, cancel. 13 over 4 times a third. Looks like that's 13/12. Okay, there. Let's also talk about our 1/2 base 1 H1. Now remember, this is no graphic approximation. These are exact, everything here is exact numbers. So 1/2, looking at that right triangle there on the left, that base goes from 5/8 to 1. That would be 3/8 in length. The height starting at the x-axis up to that y-coordinate, that's 1/2. Okay, so this gives us, no cancellations, okay, 3/32. The other triangle, 1/2 base 2 h2 equaling, okay, the 1/2, that first base goes from a 1 to a 13/8. That would be 5/8 in length for that base. The height from the x-axis up to that y-coordinate of 3/2. We have no cancellations, just 15/32 left over. Alright, so these are our various sub-calculations here, making up this asterisk, bring back the results. This is then 13/12 minusing 3/32 minusing 15/32. Okay, so sort of rounding up all these subtractions, we end up 13/12 minusing 18/32. Cancel, factor of 2, it's 9/16. 12, 2 squared by 3 in other words. 16 is 2 to the 4th. Okay, LCD, 2 to the 4th by 3. This needs a 2 squared over 2 squared buildup. This needs a 3 over 3 buildup. Okay, 2 squared, 4. 4 by 13. We're up to 52 minus a 9 by 3, 27 over the 2 to the 4th by 3. 52 minus 27, let's see, that would be 27, 37, 47, 25. Nothing's going to cancel down here. Let's just multiply this. That's 16 by 3, 48. Okay, square units. Well, let's see. Let's assess the correctness. On to part C. Part C. Assess the correctness of parts A and B by examining for consistency between the two results. To assess correctness, let's go ahead and record our graphic approximation again and our calculus result that we just obtained. Okay, and to compare apples to apples, let's get some decimal approximation to this 25/48. Okay, 24/48 would be exactly 1/2, exactly 0.50. 1/48, that's really close to 1/50th. That means 0.02 more. So this is about equals to 0.52. Okay, let's see. We compare here. This looks fantastic, actually. Let's see. A 0.05 would be 10%. We've only got a 0.02 difference. We have got these two results that are within 5% of each other. So they're consistent, and therefore the solutions to parts A and B are likely correct. Okay, looks great. Done.